Hi everyone. In the last lecture, we have discussed about another division of the spectrum into smaller parts of the spectrum, and especially we discussed about the approximate point spectrum and the compression spectrum. Now we want to discuss some important properties of the approximate point spectrum. So we want to prove the following result: theorem. Let T be a bounded operator defined on H. Then the boundary of the spectrum of T is contained in the spectrum of T, approximate point spectrum of T. Okay. To prove this lemma, okay, I am repeating again. To prove this theorem, we need an important lemma. So let us fix some notations before proceeding to the lemma. So let us take lambda in the resolvent of T. Then we know that T minus lambda I inverse exists and it is a bounded operator. So we write this operator as R lambda of T. This is T minus lambda I inverse. Now if mu is also an element of resolvent of T, then we can look at R lambda of T minus R mu of T. This is T minus lambda I inverse minus T minus mu I inverse. This can be written as R lambda T multiplied by T minus mu I minus T plus lambda I multiplied by R mu of T. So here we use the following result. So let me recall. If A and B are elements of Untitled algebra, and A and B are immutable, then we know that B inverse minus A inverse is nothing but B inverse multiplied by A minus B multiplied by A inverse. Okay, now B of H is a unital Banach algebra. So using this we can conclude that therefore R lambda T minus R mu of T is nothing but R lambda of T multiplied by lambda minus mu multiplied by R mu of T. So this equation is known as resolvent equation, or it is also known as the Hilbert's equation. So let us call this as star. And the operator R lambda T, so this is also known as resolvent operator. Okay, now let us state the lemma in terms of the resolvents. Let T be a bounded linear operator. And lambda n is a sequence of elements from the resolvent of T such that lambda n converges to some lambda which is a complex number, and not only that, R lambda n T is uniformly bounded. Then we can conclude that lambda is in the resolvent of T. Okay. So if you have a sequence of elements from the resolvent set such that lambda n converges to lambda, and if these operators are lambda n T, this sequence of operators, if they are bounded, then we can conclude that lambda is in the resolvent of T. So let us prove the lemma. So let us take natural numbers m and n in n. You want to claim that R lambda n T is Cauchy sequence in B of H. You know that B of H is complete, hence we can conclude that this is convergent. Now using that limit, we can get inverse for T minus lambda I. Okay. So let us consider R lambda n T minus R lambda m T is nothing but norm of R lambda n T multiplied by mod lambda n minus lambda m multiplied by norm of R lambda m T. This is by star, the resolvent equation. Now we know that R lambda n is bounded. So let us take m is supreme of norm of R lambda n of T, where n is ranging in n. R lambda n T minus R lambda m T is less than or equal to m square multiplied by lambda n minus lambda m. You know that lambda n is convergent, hence it is Cauchy. So from this we can say that this goes to 0 as mn going to infinity. So this implies R lambda n T is Cauchy. So let us define S as limit of R lambda n T. Now we claim that S is nothing but inverse of T minus lambda I, or we can say that S is R lambda T. So we have T minus lambda I into S is limit n tends to infinity T minus lambda n I multiplied by R lambda n T. But this is nothing but identity, because T minus lambda n into I into T minus lambda n I whole inverse, that is identity. Similarly, so we can check that S into T minus lambda I. So therefore we can say that lambda is in the resolvent set of T. So this completes the proof of the lemma. Okay, now using this lemma we want to show that the boundary of the spectrum is a part of the approximate point spectrum. So let us look at the proof of the theorem. Okay, let us take lambda in the boundary of the spectrum of T. Then we can actually, then there exists a sequence lambda n coming from resolvent of T. Because lambda is a boundary point, we can get a sequence from resolvent such that lambda n converges to lambda. Okay. Now by lemma, since lambda is in the spectrum, we can apply this lemma. So we have a sequence lambda n from the resolvent such that lambda n converges to lambda. So if lambda then if r lambda n T is uniformly bounded, we conclude that lambda is in resolvent of T. But we know that lambda is outside the resolvent of T, so we can conclude from this lemma that r lambda nt is not bounded. So by the earlier lemma, r lambda nt is not bounded. So by the definition of operator norm, hence there exists a sequence. For each n we can get xn, hence for each n in n there exists xn in H with norm xn equal to 1 such that norm of r lambda n t at xn is bigger than n. Let us call this inequality as 1. Okay, this is by the definition of r lambda nt being not bounded. Okay, so define yn as r lambda nt acting on xn divided by norm of it. Then we can say that norm of yn is 1. Now we want to show that this yn is a sequence such that norm of t minus lambda I acting on yn goes to 0. So consider norm of t minus lambda I acting on yn. So this is nothing but norm of t minus lambda n acting on yn plus norm of lambda n minus lambda acting on yn by triangle inequality. Now t minus lambda n identity into yn is nothing but r lambda n tn. So you will get this as norm xn by norm of r lambda nt xn. But we know that norm xn is 1, so this is 1 by norm of r lambda nt xn plus mod lambda n minus lambda, because norm yn is 1. Now by inequality 1, so this is less than 1 by n plus mod lambda n minus lambda. That means this goes to 0 as n tends to infinity. So we have shown that there exists a sequence of unit vectors yn such that norm of t minus lambda I yn goes to 0. So therefore we can say that lambda is in the approximate point spectrum of t. Okay, so this completes the proof of this result. So as an example, let us look at an example. So we have looked at the left shift operator L from L2 into L2, L of x1, x2, x3, so on is defined by x2, x3, x4, so on for every xn in L2. This is the left shift operator, and we have seen that the point spectrum of this operator is the open unit disk, and spectrum of L is nothing but the closure of the disk. Now, by the earlier result, by the theorem that we have proved, we can conclude that boundary of the spectrum of L is contained in approximate point spectrum of L. So that means that boundary of the unit disk, closure of the unit disk, or we can say that it is the circle is contained in approximate point spectrum of L. Okay. But we know that point spectrum also is included in the approximate spectrum. So as point spectrum of L is contained in approximate point spectrum of L, so we can conclude that the whole disk is contained, closed unit disk is contained in approximate spectrum of L. And anyway, this is subset of spectrum that is closed unit disk. So then, therefore, we can say that approximate point spectrum of L is exactly the closed unit disk. Okay. Now, we approximate point spectrum of the redshift operator. Redshift operator on L2. Okay. Now let us discuss property of the approximate point spectrum. We have the following result. Theorem. Let T be a bounded linear operator defined on H. Then the following are equivalent. There exists lambda in the approximate point spectrum of T such that mod lambda is exactly norm of T, and this is equivalent to the fact that norm of T is exactly the numerical radius of T. This is nothing but supreme of modulus of inner product X with X, where X is coming from the unit sphere of H. Earlier we have discussed about the definition of numerical range and numerical radius, and we have shown that for a self-adjoint operator, the numerical range and numerical radius are same. Okay, so let us look at the proof of this one. 1 implies 2. Suppose there exists lambda in the approximate point spectrum such that mod lambda is exactly norm T. Now by the definition of approximate point spectrum, so choose a sequence xn in the unit sphere of H such that norm of T minus lambda I acting on xn converges to 0 as n tends to infinity. Then we have the following: modulus of inner product t minus lambda I xn modulus is less than norm of t minus lambda I acting on xn, and norm xn anyway 1, so this goes to 0 as n tends to infinity. So this implies that t xn inner product minus lambda goes to 0. That means as n tends to infinity. But we know that inner product txn with xn is an element of numerical range. So we have modulus of inner product txn xn is less than or equal to omega t, and omega t anyway less than or equal to norm t. Now this is true for every n in n by the definition of the numerical range and numerical radius. So now we know that as inner product txn with xn goes to lambda, so modulus goes to modulus of lambda. So this implies mod lambda less than numerical range of t less than or equal to norm t, or we can say that numerical radius of t is exactly norm of the operator. Okay, this proves the fact that 1 implies 2. To prove the fact 2 implies 1, let us try to look at the other way. Proof of 2 implies 1. So assume that numerical radius of t is exactly norm of t. By the definition of numerical radius, it is supreme of modulus of inner product tx with x. X is coming from the unit sphere of h. So we can choose a sequence xn from the unit sphere of h such that modulus of inner product txn converges to numerical radius or norm of t. Okay. Now from this sequence we can extract a subsequence. So we can choose a subsequence xnk of xn such that inner product t xnk with xnk converges to some lambda with mod lambda equal to norm t. Okay, so we got a subsequence with this property. Now we want to show that this lambda is in the approximate point spectrum. The claim lambda is in the approximate point spectrum of t. So consider norm of t xnk minus lambda xnk square. This is nothing but inner product t xnk so this is norm of t xnk square, and the last term is mod lambda square, and middle terms you will get 2 real part of lambda bar inner product t xnk with xnk. Now t xnk less than or equal to norm t into norm a square. So this is norm t square or mod lambda square plus mod lambda square minus 2 real part of lambda bar inner product t xnk xnk. Now inner product t xnk with xnk converges to lambda. So we can say that this converges to 2 mod lambda square minus 2 lambda bar into lambda, so mod lambda square, it is 0. So therefore we can conclude that lambda is in the approximate point spectrum of T, and we know that mod lambda equal to norm T already. So from this we can conclude that there exists a lambda in the approximate point spectrum of T such that mod lambda equal to norm T. There are important consequences for this result. We'll discuss those results at a later stage. We'll stop here. Thank you very much.